Okay, here we are in lecture 7. We are going to see today the Fourier transform. So remember, last lecture we worked with the Fourier integrals, and today we are going to see this Fourier transform. Okay, so as I was saying, we saw in lecture 6 the Fourier integral representation of a function f of x, and that was given by this integral from 0 to infinity of these functions a and b of omega multiplied by cosine and sine respectively. So this was our Fourier integral representation, where we have some formulas to compute a and b. Both have the same 1 over pi in the front, and then we have these improper integrals from minus infinity to infinity of the function f times cosine of omega x in the case of a, capital A, and sine omega x in the case of b. So we are going to rewrite this Fourier integral representation using the complex exponential function. Okay, and once we have this expression written with the complex exponential function, we will see which part of that expression is the Fourier transform of our function f. So that's the goal of this first part of the lecture. Okay, so for simplicity, assume f is continuous at x, and we have an admits a Fourier integral representation. Then we know that the function f is exactly its integral representation, Fourier integral representation, because we are taking a point where f is continuous. And we know these guys, a and b, we know how to compute them. So we split this integral and we replace a and b for its values, which are this 1 over pi, this improper integral with cosine, and 1 over pi improper integral with sine. So we are just rewriting this with the information that we have. We started with a point where f is continuous, so we have this identity. This is just the Fourier integral representation. Then we just split this sum and we replace a and b by its formulas. And here is where we are. Now we can put together some stuff, like this guy could go here and so on, and we rewrite this in this way. So we have this integral coming from the Fourier integral representation, and this improper integral coming from the definition of the function capital A of omega, and similar here but with b. And we will use in this green part, of course, a trigonometric identity where we have cosine of someone and cosine of another someone plus sine of these guys repeated. This we have a magic trigonometric identity to replace the sum of these guys by this cosine of omega x minus omega t, that of course can be rewritten in the way like, okay, this omega is a common factor, so we can write exactly this. So what we have is, this is what we have used. Cosine of alpha minus beta is this formula here, and we take alpha equal to omega x, beta equal to omega t, and we get this expression. So our function f is 1 over pi, and this improper double integral in in omega and in t and omega. Okay, now remember that our goal is to rewrite this f, and to be honest, instead of the f, it's Fourier integral representation with the help of the complex exponential function. So now we pay attention to this cosine and recall Euler's formula for complex numbers, like this formula. So the exponential to the power I alpha, it's where alpha is a real number, is cosine of alpha plus I sine of alpha. And using this formula, we can rewrite cosine and sine in terms of the complex exponential. So here we make a pause, and now we are going to rewrite cosine of alpha and sine of alpha in terms of the exponential, complex exponential function. So that's exactly what I say here. If you consider the exponential to the power I alpha plus the exponential to the power minus I alpha, this is just the definition. And now, of course, we are going to use that cosine is an even function, and sine is an odd function. So this minus goes out, and this guy disappears. So finally, in the second step, we can kill these guys. And we have 2 times cosine of alpha. So cosine of alpha will be exactly the average of these two guys, what we have here. So this would be useful to this in this lecture. And here, let me see, have a minus here. So now if we do the same calculation but with the minus, we have a minus here and a minus here. Again, we use that cosine is even, sine is odd. And once we do one more step, we can kill these cosines, and we get that 2i sine of alpha is equal to this subtraction here. So we can write sine of alpha in this way with the exponential function. Okay, let's go back to our computation. We were trying to rewrite the function f and its Fourier integral representation in terms of the complex exponential function. So going back to our computation, we want to jump from integral to complex exponential function, also with integrals. So we already got this identity, f of x equal to 1 over pi, and this double integral with this cosine. And then here, remember that we made the pause and try to rewrite cosine of alpha and sine of alpha in terms of the complex exponential function. So now we are allowed to rewrite this piece, this cosine, as this guy, just using what we just saw. Okay, so we replace this cosine with this exponential, complex exponential function, and also we can split these guys, this sum, and the 1 over 2. So now we have the 1 over 2, the 1 over 2 with the pi also in front, and this sum is split already. And here we have the first exponential and the exponential with the power with the minus. Okay, so observe that we can make a change of variable here, which is done here. So we substitute in the second integral this minus omega with tilde omega, and then what we get is this differential. And also, if we were going from 0 to infinity, then this new guy, tilde omega, goes from minus infinity to 0. Okay, So this second integral, as I just said, we can make this substitution with omega tilde, and now this minus omega becomes this one. We have this we have a minus that is not written here because these guys minus infinity and 0 are already in the right way. You can complete the details of this computation, but it's not hard, it's just this substitution. Okay, so now putting together all the information, because now the name of this guy doesn't matter, it can be called tilde w omega or omega again or m or whatever, any variable that you want, but the nicest choice is to go back to omega. So we go back to omega and we had exactly like something super similar to the first integral. So what we have then is so that f of x was the first integral that we didn't do anything once we replaced the cosine with the complex exponential function, and the second integral we did this change of variable and we get this expression. And now if we pay attention to these guys, we are going from 0 to infinity in the variable omega, but we are also going from minus infinity to 0 in the variable omega. So then, and we have the same guy inside the integral. So what we are really computing here is, well, the factor is the same in the front, is the double improper integral from minus infinity to infinity of this guy, f of t, and this exponential. Okay, now we are almost in achieving our goal. So now we can distribute these guys and rewrite this expression with these two terms. And we can also distribute, let's say, this 1 over 2 pi into these two guys, 1 over square root of 2 pi times 1 of a square root 2 pi. And we rewrite this expression where we split this 1 over 2 pi in these two factors, and we distribute this exponential with this first term, let's say, and this second term here. And I think there is a minus missing here. Okay. So this guy that we have here is what we call the Fourier transform of f. Okay. Okay, going back then to our expression, so we have f of x equal to this huge guy that we rewrite this guy in this way, and this purple thing is that we call the Fourier transform of f. So this is the complex form for the Fourier integral representation of f. Well, sorry, this is the Fourier transform of f, and this whole guy is the how we rewrite the Fourier integral representation into the complex exponential expression. Okay, so definitions. This is a definition. This hat f of omega, which is this purple part in the previous line, is called the Fourier transform of f. Sorry. And here there is a minus missing. Be careful. Okay, now it's okay. Sorry. Okay, so this is the Fourier transform of f, and we have this notation with the hat, and this is the inverse Fourier transform, where we have this hat here, the function with the hat here. We can also give this another notation, which is this weird f. So we have this f of omega, the Fourier transform of little f of x, or the inverse Fourier transform of g, the inverse Fourier transform of g, with this notation. Okay, so usually this f is a function of x, and once we transform it, we get a function in omega. And this function g is a function of omega, and when we inverse transform Fourier transform this g, we get a function in the variable x. Okay. When we want to be more specific, we can also write what I just said in law, like the Fourier transform or a function f of x gives a function in omega. So this is the Fourier transform. And if we have a function g of omega and we inverse Fourier transform this function, then this guy is a function in the variable x. Okay. So we saw in lecture 6 that when a function f of x admits a Fourier interval representation, then both coincide at points of continuity of the function f. At points of discontinuity of f, the Fourier integral representation takes the value, again, the average of the right and left limits of f of x. So this property, now in the setting of Fourier transform, can be written, where here is just recalling the definition of the right and left limits. So in this setting of Fourier transform, these properties become our Fourier transform is equal to f if f is continuous at x, and if it's discontinuous, we have this average. Okay. So observe that the inverse Fourier transform is an improper integral of this, because we have this minus infinity and infinity here. So it might not exist. We don't know. Okay, so just to remind you that we understand this type of integrals as the limit of f going to infinity. You can take a look at the first part of lecture 6, the auxiliary notes. So we take the limit of m going to infinity of these proper integrals between minus m and m. So we saw in this lecture 6 that we can use Fourier integral representations to compute some improper integrals. And okay, so for example, we use the Fourier integral representation of f of x equal to 1 in the interval minus 1, 1, 0 outside, to find the value of the improper integral sine of omega or divided by omega between 0 and infinity. And you can check the lecture 6, it was pi over 2, the value. So now we can do the same in this new setting of Fourier transforms. For instance, if we choose omega equal to 0 in the identity, the Fourier transform of f equal to just the definition, choosing omega equal to 0, this exponential becomes a 1, and while here we have a 0. So what we get is that the Fourier transform of f at 0 is this integral. The integral from minus infinity to infinity of f of x multiplied by this factor 1 over square root of 2 pi. Okay, so when our function f is positive for every x, this guy is just the area between the axis x and the graph of the function f. So this value, the value of the Fourier transform of f at 0, gives us the value of the area between the graph of f and the x-axis, multiplied by this factor. Okay. And this is just a picture to illustrate what we just said. We have a positive function here, and all this purple stuff here is just this integral. And when we multiply by this factor, we get the Fourier transform of f at the point 0. Okay, that's all for this first part. In the second part, we are going to see some examples.